Today, I want you to take a moment, take a look at these three functions of two variables, and describe what you can see using contours or level curves. We know that each one is a function of two variables, so we are trying to represent a surface in R3. So pause the video here, take a moment, and describe level curves. Welcome back. So we want to look at the contours and level curves, and in the first two, we can see something that stands out. We see this x squared plus y squared structure. One of them is just sitting by itself, and the other one is inside of a square root. What this tells us is that we will be looking at circles. So that x squared plus y squared should jump out at you. It's like from one direction, we're going to be looking at circles. We saw that yesterday with the x squared plus y squared equals r squared. Even the square root of x squared plus y squared, remember what we're doing. We're thinking about level curves. We're picking a constant for one of the variables and seeing what curve we get. So remember, when we're looking at level curves, we're going to assign one of the variables a constant value. So we're going to give one of the variables a constant value. And then we're going to see what curve results. That's the important part. So for these first two, if we let z equal 0, that's a value that we could have for z. So what if we make z equal to 0? Then our equation becomes x squared plus y squared equals 0. And the only way that's going to happen is we get 0, 0. Our curve is just the origin. All we get is a point. And that happens in the other one, the second one as well. If we make z equals 0 here, then our equation is going to be the square roots of x squared plus y squared equals 0. So we're also only going to get 0, 0. We'll come back to this linear one in a minute. We want to pick some other values for z. So I'm going for contours on these first two. Once we get an idea about what's going on, then we'll start looking at it from the side. So let's, for each of these, pick z equals 1. So the next contour, if we pick z equals 1, in this case, we're getting the same circle, because 1 squared is just 1. If the square root of x squared plus y squared is equal to 1, that must mean x squared plus y squared equals 1. So in both cases, we have a circle of radius 1, centered at the origin. Both of these surfaces have the same contour. Circle of radius 1 centered at the origin. So at a height of 1 above the XY plane, in both cases, the slice we're looking at is a circle of radius 1. So let's check contours for z equals 2, where things are going to change. Over on the first one, we're looking at a circle of radius square root of 2. But on the square root version of things, we have a circle of radius 4. So now at a point 2 units above the XY plane, the non-square root one has a circle of radius square root of 2, about 1.4. But the square root version has a circle of radius 4. So it looks like the second one, the square root one, has expanded more than the first one. Everybody see it? Not worried whether you can see the actual thing. We're just looking at the contour. Square root of 4, radius 2. Thank you. So over here on the non-square root one, we have a circle of radius square root of 2. But on the square root one, we have a circle of radius 2, not 4, like I said earlier. Very good. You found my carefully planned mistake. That's 0 points for you and minus 10 for everybody else. I'm just kidding. It's minus 10 for everybody for letting that happen. I'm just kidding. There's no way I can just keep trying it out. What's funny is I was sitting there thinking, my God, that's going out way too fast. There's something wrong here, but I just ran with it anyway. Yeah, someone will stop me. So we can see that, oh, calm down. I don't know if you've noticed it, but the robot apocalypse has already begun. We don't need anthropomorphic robots to take over the world and start messing with us. It's already started. The technology is always messing with us. Like the pens are like, oh, we're not going to work tomorrow morning. But we're going to be fine, like in the evening before. It's like, well, yeah. When we test the pens, everything's going to be awesome. But tomorrow, when class starts, that's when we strike. Doesn't need no fancy iRobot anthropomorphic robot. It just needs like a pen. The pen's like, oh, haha, gotcha. They take out their small revenge. Oh yeah. So we can see now that things have started to change. At a height of 2 units above the XY plane, our non-square root one has a circle of radius square root of 2, about 1.4, but our square root one has a circle of radius 2. So it looks like the non-square root one has pulled in a little bit, whereas the other one has circle of radius 2. Good question. Let's do one more to see what's happening. So on our non-square root one, I end up with x squared plus y squared equals 3. We have a circle of radius square root of 3, about 1.7. But on our square root one, when z is equal to 3, we have a circle of radius 3. From the top, we're just seeing a bunch of concentric circles. In the non-square root one, we see those circles getting closer together. On the square root one, they're evenly spaced. The radius just keeps increasing as we take steps up 1z, up 1 in the z direction. The circle's radius goes up by 1. If z equals 4, the radius will be 4. Z equals 5, the radius will be 5. The radius is increasing in direct proportion with z. It's the same value. But we see that the concentric circles in the non-square root one are getting closer together as we go up. With the first one, we go from 0 to a 1. And then in the next plus 1z, we went from 1 to 1.4. And then in the next plus 1z, we went from 1.4 to 1.7. So they're getting closer together. You see those circles getting closer together. I could be drawing circles for you now, but the important part of the exercise is picturing the circles, not having them pictured. I need you to create these circles in your mind. So the z values in the square root version, the z values tell you what the radius is going to be. In the non-square root one, the z values tell you the square of the radius. Question? The radius is proportional to the z. The radius is going to be the square root of the z value. That's what it looks like. We didn't see that when it was 1, because square root of 1 is 1, but now when z equals 2, square root of 2, z equals 3, square root of 3, and we can see what the pattern is going to go, where this is headed. The next one will be a circle of radius 2, square root of 4, then square root of 5. It's always going to be a square root because of the way the radius works. And we're missing that over here. So what we're looking at is when we have z equals some constant, that constant is the square of the radius. Over here, that constant is the radius. So over here, when we start looking for the pattern, we see that we're looking at the z value is the square of the radius. And over here, the z value is the radius. So we see that the radius and the z value are proportional. If I double the radius, if I double the z value, I will end up doubling the radius. But over on the non-square root version, the z value that we pick is the square of the radius. Questions? Yeah. Yes, it's better to pick one variable and see how changes go with that variable. What happens if I change just that one? Once you have an idea about that, then we can do what as you're suggesting. Now let's take a look at another one and see what changes there. So yeah. Don't change too many things at once. Start simple. So this last observation here has given us some insights. Here I'm looking at z equals r squared. The z and the radius are making some kind of parabola. And here, the z and the radius is just making a line. The relationship between z and the radius is a line here. The relationship between z and the radius is a parabola here. Let's take a look at what's going on from the side, and we'll see that happen. I just remembered why I only had the 2, and I didn't want to fill the third column with this plane here. Dang it. It's because that's how the pens got me. Okay, you win this time, pens. You distracted me. Messed up my plan. So these are all views from what I've been referring to as the top. Z is going to be our up and down. X and Y is our floor. Z is our up and down. We've been looking at things from the top. From the top, we see all these concentric circles, but they're expanding at different rates. Let's look at things from the side view. So hold on, linear function. We need a side view. So I'm going to start looking at values of X. If X equals 0, in the non-square root version, I get Z equals Y squared. A parabola, its vertex at the origin. If X equals 0 on the square root version, I get Z equals Y. Right? He said, knowing that it's wrong, seeing if someone will spot it. Square root of Y squared is Y, right? Plus and minus, absolute value. Not going to give us plus and minus. It's going to give us the absolute value of Y. The square says make that negative positive. Because even exponents are your annoying friend that's always cheerful and just telling you to cheer up. So that's going to make things positive. And this square root business anyway is always going to be make things positive. But so when X is equal to 0, we're looking at a parabola. This is looking at things from the side. We're looking at just the Z and the Y. So standing on the x-axis, looking at this surface from the side, we see a parabola when X is equal to 0. Over on the square root side of things, when we stand on the positive x-axis and look at the surface, we see an absolute value graph, which is V-shaped, like a regular V, not like a rounded V, like the parabola. I realize that parabolas are V-shaped as well. I know people say parabolas are U-shaped. That is completely incorrect. U's are vertical on the sides and parabolas are not vertical on the sides. Stop describing parabolas as U-shaped graphs. That's not how you make a U. You know what I mean? It's a rounded V. A little bit picky on my part, and it's fine for algebra students to be like all U-shaped because they can't draw parabolas very well anyway, because they're new. At this point in your mathematical career, you got to be better at parabolas. They're not U-shaped, vertical sides. U. Come on. Come on. Let's get serious here. So here from the side, we're seeing a parabola. And here on the square root one from the side, we're seeing a V. The vertex of both is at 0, 0. If we pivot around the positive y-axis and look at the surface again, we'll get the same thing. Z is equal to x squared, or Z equals absolute value x. But now we know what the surface looks like from the top, and we know what the surface looks like from the sides. Let's do another one. Let's say x equals 1. So when x is equal to 1, if I like stand at the positive x-axis, look at the surface, and take that parabola and move it forward 1 square, we see that the vertex is going to go up. So we'll have a parabola again. But the vertex is now going to be at up a little bit higher. So here's our x equals 1 contour, level curve, and our x equals 0 contour will be sitting behind it with a lower vertex. So at this point, we've looked at this surface from the top and from the side using the technique of level curves. This is not a new thing that we're doing. This is just a new environment that we're doing it. We do this all the time. Every time we look at how something is changing over time, instead of looking at everything all at once, we look at in pieces. What happened at day 1? What did day 2 look like? What did day 3 look like? What did day 4 look like? Those are level curves at fixed times. And that's all we're doing here. But instead of fixed times, we're using fixed positions. We're picking one variable, looking at different values of the constant. Now, all we have to do to describe these completely and start drawing pictures is to figure out what our contour at x equals 1 looks like. But I have to do it now. If I don't tell you immediately what this contour looks like, so that you can put it all together right now and make you wait until tomorrow to draw these curves, you're going to have to go through calculus at the normal rate. Man, if I could just describe what this looks like right now, then calculus 3 will be immediately clear all the way through, even to vector calculus. I don't know how it works. It's some kind of magic, but I have to do it right now. I can't wait. So let's take care of Calc 3 right now so we don't have to go through the rest of the semester. Let's immediately know everything that I know about Calc 3 and not go through the rest of the semester. But if we wait until tomorrow, we're just going to have to do this normally. So this is, oh, look at the time. I guess we'll have to wait till tomorrow. That's it for today. I'll see y'all on tomorrow. Everybody have a good day. Think about what these look like. And thanks for playing.